Good afternoon, everybody, and welcome to the fourth session of the summer term 2026 of Sunoikisis's Digital Classics. This term is dedicated to exploring digital scholarly editions in classics, Byzantine, and medieval studies. And today's session will be dealing with linked open data in digital scholarly editions. And our speakers today are Daniele Fusi and Paolo Monella, who are true authorities in this topic. And as always, if you're watching live, that is on the, what is today, 12th of May, 2026, feel free to write in the live comment section of the YouTube video. And we always like to know where you're watching from. And of course, feel free to ask questions or leave comments that our speakers will address at the end of the session. Today, it's the structure of today's session is a bit different. We have a first part on which will be more of a lecture, and the second part which will be more of a hands-on seminar that will guide you through the exercise that you will need to do as your homework. And today I know for a fact that we have a very much to cover and too little time, so please, Daniele and Paolo, go ahead, and the floor is yours, and I will share Daniele's slides.
Introduction. And so a core task in digital humanities is defining a formal view of your subject. Data needs to be structured according to this model that is organized to be understood and processed by a machine. So for instance, consider a dictionary. Before the digital era, we had only printed dictionaries fit to humans. We can transfer the dictionary's text from paper to a digital medium using PDF, and that's essentially digital paper. If it's not just an image and its text was successfully recognized, at least we can use a full text search. Of course, looking for a word in a dictionary in this way is like finding a needle in a haystack. For instance, if you look for a specific lemma, this is submerged in a sea of other words in the text of the full dictionary. The next level in digital dictionaries was then the web. HTML, the markup language of web pages, was used to encode the layout of lexical entries. In this example, markup is the red text within angle brackets, and HTML, as you know, is presentational markup designed for the structure of a hypertext. So it says things like this is a paragraph, a title, a table, and not things like this is a lemma. Sure, a lemma can be emphasized, and this emphasis can be rendered as bold in its page, but this has no intrinsic lexical meaning. It's just style, and it's ambiguous because any other part of the text besides lemma might be bold. So even if HTML is much more flexible than PDF, we are still stuck with full text search. Then XML was created. This is a sister technology of HTML and is truly semantic. So instead of a fixed set of tags used to mark up the layout of a hypertext, in XML, everyone can define tags for any purpose. So for dictionaries in TI, which is a dialect of XML, we get tags to say things like this is orthography or hyphenation or definition and so forth. So every single portion of the text is semantically defined. And this allows powerful search, combining multiple lexical criteria, and any presentation generated by transforming XML into HTML. We need this transformation because nothing in lemma says how we want to display it, whether it should be red or bold or anything else. So that's an important point because lexical content here comes with no indication about how to present it to users. That's why we transform it into HTML, which is presentational, while XML is semantic. We have separated content from presentation, so we need to transform it into a presentation to publish it. On this way, we might even drop the text altogether and create a database with pure data. That's no longer a text talking about lexical data. It's lexical data itself, like a form with a set of fields to be filled in. This ideal form is defined by our model, which defines what we want to say about each word in the dictionary. Of course, models are approximations, so we'll never be able to nor want to say everything about everything. In a model, we just select those features relevant to our vision and intent. So consider the famous Plato span about defining the hoarseness of a horse. This is the idea of a horse above all the individual instances of it. If we want a model for the idea of a duck, we could just select features like beak, wings, and legs. And if this is all we need to define our idea of a duck, that's fine, even if the same features belong to very different animals, like chickens, penguins, or even some insects. So it's up to us to model our data according to our idea of it. The model gives our data its structure, and this allows computers to understand it, process it, and present the same content in unlimited different ways. As with XML, this means that our data is now independent of the way we present it. Content, again, is separate from its presentations. And that's much more powerful because it allows structuring the content according to its intrinsic semantics, like lemma, hyphenation, meaning, rather than to its appearance on a web or a printed page. And additionally, we get as many presentations as we want from the same source, which is created only once. So we have outlined the dictionary's history from paper to its digitized counterpart, and then further into HTML, XML, and possibly databases, constantly improving the semantics. Now, the dictionary example is interesting because its evolution mirrors that of the web itself up to semantic web. Web 1, as you know, was a web of hypertexts. There we just had a bunch of static web pages with some text in a given language. You wrote them and you published them. This was data for human readers, not for machine consumption. With such a low data structure, we had a notion of words to search in a search engine, with all the limits posed by natural language. So when interested in Epic, we searched for Homer, but we ended up with The Simpsons. Then Web 2 transformed this network of documents into a network of applications. Think of sites like Amazon, Gmail, Google Maps. These are highly interactive software applications, fetching data from some sources, typically a database, and providing them to the end user. Again, here content, that is the data in the database, is separated from its virtually unlimited presentations. And software stays in the middle, generating web pages and modifying them as it interacts with users. HTML here defines a user interface rather than the layout of a text. And then CSS styles give it its appearance, and JavaScript code defines its behavior. The result is a much smarter web, which anyway is smarter thanks to these software applications and their data, and not for the infrastructure itself, that is the web, which is always the same. Of course, there are a lot of database types and implementations to be used here. Most of these types share a common abstraction, but each implementation is independent, and digital formats are not compatible, so they can't be directly exchanged. We can convert one into another, but this can be either trivial or very complex according to the scenarios. And more important, whatever the type, each database has its own underlying data model, which can be completely incompatible with others. And finally, software is usually tailored to each combination of type, vendor, and model. So this makes the web of applications also a world of data cages. For instance, among these types, one of the most popular databases is the relational one. The relation essentially is a way of saying something about something. So its typical implementation is a table. For instance, if its row is a person, then its name column tells the person's name. So the row is the record, our person, and the column is an attribute of that person, in this case, the name. So for instance, here the first row is saying that the person has name Bob. A relational database has many tables like this, each defining a specific set of relations for entities. So every database has its own set of tables, which implement its own model. And remember here the duck and the penguin. My tables about birds may define records and attributes which can be completely different from other databases. I am the one who decides which entities to define and which are their attributes, like birds, their names, or their colors. So we end up with incompatible models. Other databases might have totally different tables with a different selection of attributes. And additionally, each row would be identified using keys valid only within that database. For instance, I might use a number for each bird, but this convention is valid only inside that database. Outside of it, this number is meaningless. Other databases might use the same number for any other entity. So data in a database has a really high level of structure, but it's caged inside its boundaries because each database uses different structures. So for better integration at a global level, we need to break out of these cages. And as always in the history of web, we don't start from scratch. There already are many data distribution strategies for databases. When databases are very large and performance is critical, we distribute them across several machines. So say we have a relational database with data about Marco Polo and his family. Here rows represent persons and columns their attributes. Now we want to distribute this database across many different servers in the world. So to start with, we can distribute our table by rows. That is, each server holds a certain number of rows. So for instance, server A contains Marco Polo and server B, Niccolo and Maffeo. This implies that both servers must have their own copy of metadata about columns, like their names, so that all servers know that column 1 is the identifier, column 2 is the name, column 3 the birth date, and so forth. So in this case, we share metadata, which are the names of the fields in the tables. Inversely, we can distribute our table by columns. In this case, each server has a certain number of columns. So server A maybe contains ID and name, while server B, birth date and place. This implies that both servers must have their own copy of the identifier column so that we can refer columns in different servers to the same row. So here Marco's identifier is 56, and it must be present in both rows, both in A and in B. This is what joins data about Marco together from different servers. And so here we are sharing identifiers. Finally, we can do both things, distributing by cells. Each intersection of a row and a column, that is a cell, becomes a separate record. So server A contains some of these cells, maybe Marco, Niccolò, and Maffeo, and server B some other cells for birth date and place. So that's the highest atomization of data, which requires sharing both metadata, that is column names, and identifiers, here the numbers which identify rows. So each record must have 3 elements: its row identifier, here the numeric ID, its column name in the corresponding table, and the value at their intersection, that is the cell's value. So what do these cells say? 56 has name Marco Polo, has birth date 1254, and has birthplace Venice. The first statement happens to be in server A and the others in server B. Data is completely atomized and distributed. And again, 12 is name Niccolo Polo, has birth date 1230, and has a birthday place Venice. And finally, 35 has name Maffeo Polo. So if we focus on these statements, the cells, independently from the tables which contained them, we can break the single database cage. We thus define a new structure, this set of three parts, named triple, a subject, a predicate, and an object. The triple is no longer inside the cage of the table. It floats in a cloud distributed across servers and connected with other triples building a giant graph. And that's precisely the foundation of semantic web. Subject, predicate, and object build our statement, which tells something about an entity. Now, these examples belong to a controlled database, so they just use numbers to identify entities and arbitrary names to identify attributes in each table, the field names. But in a global database, we need global identifiers. Any subject, predicate, or object, when it's not a literal value like the year of birth, but an entity like Venice, must have its own global identifier. Otherwise, people won't be able to build statements about the same thing. We need to identify this thing as the same in a global context in order to use it. Yet we can just use a name because this depends on a given language and it's ambiguous. Remember Homer and The Simpsons. Also, the numeric ID is not a solution. The web is open and it would be crazy to imagine a central authority assigning numbers to each thing. So how do we get these identifiers? Now an answer comes from the existing web. There we identify each page from its address, and that's the URL, that is the Uniform Resource Locator. It tells the browser how to reach that page, but it also uniquely identifies it. In fact, when you enter a URL in your browser, you land to that specific page and nowhere else. So a URL also works as a more general identifier, which is called URI, that is Uniform Resource Identifier. So a URI identifies something, while it tells nothing about how to reach it, like the URL does. The URI is like my name in this virtual room, because it uniquely identifies me, but tells nothing about how to reach me. So just like we forge a URI for any web page, we can forge a URI for any entity. The same authority which ensures that my domain in the web is unique will be used to ensure that my identifiers are unique at a global level. For instance, here you see the URI of Marco Polo in DBpedia, which is the semantic web version of Wikipedia. And note that often you can even reach a page when entering a URI like this in the browser. But that's just a common practice, not a requirement. Even if a URI looks or acts like a web page address, a URL, it's not that. It's just an identifier. So we are simply using an existing web technology to get the identifiers we need. This way, the existing web infrastructure provides the solution, and just like pages, everyone can publish data about everything without risks of collision. Thus, any subject, predicate, and object are identified by their own URI. In our database sample, we had numbers as row identifiers and names as column identifiers, like name for a person's name. Here instead, we have URIs for everything. The only exception is a literal object because it's just a simple value, like a text or a number. At most, literals have their data type specified, which tells us whether it's a string in a specific language, a number, a date, and things like that. So for instance, in this triple, the URI for Marco Polo in Wikipedia is the subject, while the URI for his name is the predicate, and the literal value for it in Italian is Marco Polo. Any other data can be attached to Marco Polo in the same way. So his father, birth date, birthplace. We keep the same subject and use new predicates and objects. Predicates are the links which connect nodes together in this graph. So this implies sharing a set of vocabularies which define all the concepts used as subjects, predicates, or objects, each with its own URI. And these vocabularies are known as ontologies. There are a lot of them available, covering very different domains. Some are general purpose, like Dublin Core, which is used to define generic metadata like title, description, creator. Others are more concept specific. For instance, FOAF is used to describe persons and their activities. And anyone can create ontologies, but of course, we want to reuse concepts from others without having to reinvent the wheel each time. So we have our triples and their vocabulary, and we can now build a network with them. Triples can be connected each other without any limits, building a network of nodes, each representing an entity. And that's the graph of the semantic web and the model of this sort of global database. By working this graph, we can serve any knowledge domains and even let machines infer data on their own. So say we start from the Socrates node. He is a man. In turn, a man is a class of beings defined as a subclass of animals. And animals belong to the class of mortal beings. And from this fact, the machine can infer that Socrates is mortal, even if this is not explicitly said in the graph. Now, that's a trivial inference, but think of millions of nodes and of all the inferences and new connections which can be done from it. So if we continue, for instance, an ox is an animal too, and an ox eats grass. Grass has color green, and Frankenstein has color green too. So here we walked seamlessly from Socrates to Frankenstein via green things like grass, which are eaten by oxen, which are animals like man, Socrates being a man. In this giant graph built by connecting all the smaller graphs published on the web by each person, we can walk from any concept to any concept. So that's a global database directly published for machine consumption. Let's make a more realistic example. Marco Polo here is URI, and he has various names according to the language used. He is a person, and the concept of person has its URI too, like any other node. He was born in 1254 in a place, and this place has name Venice in English or Venedig in German. Also, Marco Polo is an Asia explorer. So all entities have their URI identifier, as you can see. And anyway, as URI are really long, we usually shorten them. Shortening URIs is done in a very simple way. We just replace their first portion with an arbitrary prefix, like this. Here we picked a prefix for the first portion of each URI, followed by a colon. And this shortens our identifiers and makes them much more readable for humans. So in this context, a name with a prefix is known as a qualified name, or QName for short. And now, as above for Socrates, we can link Marco Polo to any other concept. So for instance, consider the Wikipedia, which is the graph of nodes extracted from Wikipedia text. In the Wikipedia, Magellan is an explorer of Asia, like Marco Polo. Venice is located in the Venetian lagoon. Julia Lama, a paintress, happened to die in Venice. Anthony Quinn, an actor, was a person, just like Marco Polo and billions of others. And Alpi Eagles was an airline company having its hub at Venice. So all these connections of very different things can be automatically done by just walking the DBpedia graph. And in turn, this graph gets connected to any other graph published in the web, thus building a giant global graph of pure data. So publishing data on the web will no longer be publishing their presentations in the form of hypertext or user interfaces built for humans. This is what happened in Web 1 with its static hypertext and what's happening in Web 2 with its applications, interacting with underlying content. In Web 3 instead, we publish data representations. That is, they are models in the form of triples for machine consumption. We no longer rely on a myriad of separate databases. There is a web infrastructure providing a universal model so that data can be consumed directly. And the model behind triples is known as RDF, that is Resource Definition Framework. With it, any data published gets merged into the global data graph. So we no longer have to painfully extract the data from hypertext designed for humans using a traditional search engine. We rather have data directly modeled using a universal scheme independent from any specific human language. So that's a sort of global database with a universal scheme yet based on our old web technologies. And all the technologies and practices involved in this scenario are known as linked open data, or LOT for short. We thus got to the top of this ideal pyramid, freeing data from their cages with LOT. And note that this was a progressive evolution. And even today, this doesn't imply that you are going to create your data directly in RDF. Rather, often you start from a higher level perspective, like the entities of a database or those scattered in a TEI text, and then project or link them into LOT. In fact, each step of this evolution was the condition for the next one, and Tim Berners-Lee has summarized it with a 5 stars evaluation of published data, where each step includes the previous one. So 1 star is when you start and just put something in the web, like a PDF table. Data is locked in that format, like in our PDF dictionary. Then 2 stars is when you rather use a structured format, like Excel. This makes data in the table usable by machines. Think of all you can do with numbers in a spreadsheet. 3 stars is when you move to a standard open format, like from Excel to CSV. The legacy Excel format was a proprietary one and belonged to Microsoft, and thus not a standard nor open, while CSV is just plain text. 4 stars is when you globally identify each entity, that is, in our case, each row in our table. And this is required if you want to publish them globally, so that everyone also can refer to any of your entities without ambiguity. And finally, 5 stars is when you put this data in context, linking it to other data. And that's why we needed global identifiers. So we started with the dictionary example. Now in LOT, the most popular lexical ontology is lemon. So let's see how it works to see how words look in it, so we can see something more relevant. Say we have the Italian word vitello, the young cow. It can have 1 or more written forms and sound forms, and that's the side of its morphological expressions. On the meaning side, instead, vitello has a couple of lexical senses: the living animal and its meat. Of course, all these senses in the end refer to the abstract entity we think of for this word. So that's an abstract concept existing regardless of the specific language, a sort of Platonic idea. Also, as for the Italian word, we can say that both these senses, the animal and the meat, are covered by an overarching lexical concept. And that's why we have a single lexical entry in the dictionary instead of 2. In turn, this lexical concept can be made part of a larger set of lexical concepts sharing a common domain, like for instance, different types of young animals and their meat. So this model accounts for the relational nature of meaning in lexicon and can best be seen by looking at another language. In fact, the same entity in English has not one but two words because their lexical senses are split. Calf is the living animal, while veal is the meat. We thus have two sets of semantic features which don't perfectly align. In language, meaning, of course, is a relational feature. The semantic boundaries of a word are defined by its surrounding words, and each semantic feature of a word is computed based on context in corpora, creating a complex graph of relations. So this model underlies lemons entities, and the lemon ontology has URIs for all of them and defines their relationships, so we can build a full dictionary with triples. So we started with a text on paper, and we ended up with a graph of nodes. And that's exactly the architecture of the RDF model in LOT. The lemon ontology provides a vocabulary for lexical data, so it's just one of the many ontologies we have. In it, our content is completely emancipated from its traditional presentation in the form of a text, even beyond the boundaries of a specific language. So words and concepts are all identified by their global URI, and this allows cross-linking lexical resources from many different dictionaries, even from different languages, like it happens in Lila, which is a lot-based set of Latin lexicon resources whose graph can be walked from node to node, crossing language and time boundaries. So after all this introduction, let's see how RDF looks like in practice. RDF is our abstract data model representing the graph we have seen. We need a digital format to represent it and store it. And in fact, there are many formats for different usages. One of the most popular human-friendly one is Turtle. Turtle is just plain text, so it's very easy. And writing it, you can represent a graph. In Turtle, we put URI, our entity identifiers, between angle brackets. Also, we can shorten them using a qualified name, as seen before. And all the prefixes used must be defined at the start of our Turtle document, like here. Finally, all terms which are not a URI are literals and are wrapped in double quotes. Optionally, they can be followed by a suffix which represents the type of the data. For instance, you can see that 123 here is an integer number, and the other sample value is a date. And also, one of the most used predicates is RDF type, which says that a subject is of a specific type. In Turtle, we can shorten it with just this a, because in common statements, you say things like Marco Polo is a person. So this a in is a shortcut for RDF type. You will find it a lot of times in Turtle texts. So let's now see the statements built from these terms. Like in our language, statements are ended by a stop in Turtle, and multiple statements sharing the same subject can be connected with a semicolon. If they also share the predicate, they can be connected with a comma. So here, Marco Polo is the subject shared by three triples, and they tell us that this entity is a person and has a couple of labels attached, providing his name in two different languages. So here is how we can represent some data about Marco Polo with Turtle. First, we define some prefixes. Then our subject is Marco Polo. He has a couple of labels in two different languages. And again, note that here we are dealing with higher level concepts, not with linguistic labels. We are free to attach to each concept as many labels as we want in any language. We then say that he is a person, and notice the A shortcut, which stands for RDF type. Also, he has a birth date, which is a literal value, and a birthplace, which is another URI assigned to the place we call Venice. And finally, it belongs to the class of Asia explorers. In turn, Venice has a couple of names in different languages. So the whole graph depicted here can be represented in a text-based format using Turtle, much like a set of linguistic statements. Now let's have a peek also at querying data. Just like SQL for relational databases, in LOD we have a query language which is named Sparkle. And you can see an example here, but don't be afraid if you don't get all the details, just focus on its idea. We want to get triples, and triples are statements. So we just phrase the statements we'd like to get using placeholders instead of real data. The server will fill our statement template with data and return it. So here the select portion tells what we want. It's the list of our placeholders. Here we want only Marco Polo's person with some other data. And the where section is like a set of statements representing the template to be filled by our selected data. I used here green for the subject, orange for predicates, and blue for objects. So you can see these are triples. And in these triples, the server will replace all placeholders, starting with question mark, with real data. So here we want only a person, and this will be filled in the person variable, having a name in the name variable. Optionally, if available, we'd like also to get a birth and a death date, a wiki page, a default picture, an abstract, and so forth. And we also want the birthplace and its label, and the death place and its label. And finally, we want only English labels for places. So just like in semantic web, we have a global unique model for our data, we also have a global unique language to query it. And that's Sparkle. Now, you might wonder how we can use LOD in real-world projects. Using LOD also means facing its practical issues, because, of course, there's no magical technology. Each has its own benefits and limitations. On the plus side, LOD uses a universal model designed to link data worldwide. There are a lot of well-established ontologies you can use as building blocks, and the model focuses on pure content, language independent, and built for machines. It also allows machines to reason with a deterministic foundation, like in the case of Socrates and its mortality. So it's a complement to the probabilistic approach of AI. And also it's based on existing web technologies. Anyway, a practical issue is scalability. A worldwide distributed database can quickly become so huge that queries get slow or just don't work. Performance here can be a very serious problem. Also, LOD data depends on a totally open world, constantly changing and potentially breaking your software. You are not in control of data which empowers it. This is data which is published on the web by everyone. That's another reason why you often start with a local database and then export it into LOD. And finally, when creating content, we usually need a less fragmented way of defining it. We humans don't think with a myriad of atomic, loosely coupled statements like this. For instance, consider this simple sentence about Petrarch's birth. Here we need a dozen triples and a couple of ontologies to just represent it in LOD as a set of linked atomic statements, like here. So usually scholars won't directly create data in this form. It would take a lot of time. In a typical scenario, instead, the primary purpose of LOD is data integration. So in most cases, we rather create content in more traditional ways, for instance, in relational databases or in TI or whatever, and then link or export it to LOD. So we start, for instance, from our own local data in a database or in a set of TI documents when it's text. And typically, these projects link to load ontologies for their vocabulary and authority lists. Universal identifiers ensure that we can link them to existing data, whatever their names. For instance, when a text mentions a person or a place by name, we can link it to the corresponding URI in Wikimedia or in a geographical gazetteer like Pleiades. So not only this removes issues due to language-specific names and their ambiguity and their history, it also gets more data. For example, in the N8, you can link Lavinium to a place URI, getting also its geographical coordinates. Or when you link the god's name Juno, you gain access to all data about her in Wikipedia. On the other way, some projects might export any subset of their data into various RDF ontologies. So that's not just linking your project to the load cloud, it's transforming your project or part of it into a part of the load cloud. In both cases, load works as a universal glue, which connects all sorts of projects together. Integration and long-term preservation here are key values of load. And that's why every project should consider it, even without having to directly generate triples. So enough theory, we can now play with this, and I lend the floor to Paolo.
Okay, thank you, Daniele, for this introduction to load. At some point, Daniele showed the hand of Aristotle, meaning the practicing of load, and inspired by that hand, my part will be an actual hands-on exercise in which I'm asking you to apply some of this with an exercise that mimics the real-world scenario that you have when you have a digital scholarly edition, maybe done in TEI XML, and you want to export it. You're not exporting to load, but if you want to integrate load resources, load data taken from the semantic web into your edition. So what I'm asking you to do right now is to go to the wiki page of this session 4. So I'm allowing a few minutes for you to open this page, because this is the page we're going to use for the exercise. Now, first off, the exercise is down here. Exercise, all right? And it is quite long and detailed. So I'm asking you to take your time to do this exercise in your own time, in an asynchronous manner, basically after watching this video, in full. But what we're doing during this video is a shortened version of the exercise, because I personally am not taking longer than 30 minutes. So the exercise has step 1, 2, 3, 4. We are skipping a few steps, going to the central aspects that give us an opportunity to discuss some practical application of load technologies to digital philology. So if you're bearing with me, if you're following me on this page, which you probably already opened, and you're down to exercise, we have 2 files that we can use in this exercise. When you do the full version of the exercise, we're going to start from the incomplete version of the TEI XML file and start from step 1. However, since we're doing a shortened version here live, or anyway during the video, we are now using the complete version. What is this? What is the incomplete? What's the complete version? They are 2 different versions of a TEI XML file, including the incipit of Virgil's in it. So first off, click on the complete version URL link, complete version, okay, and click on download the raw file, which is here. Download the raw file, so you can download the XML TEI file. You already know what an XML TEI file, so I'm not going over this. So I just downloaded this. It's called init complete. Again, we're using the complete version because we're doing a shortened version of the exercise. Now, this is the XML file. that I downloaded. Please open it with your XML editor of choice. I'm just using BIM. What are we doing now? For the shortened version, we're not editing the file. We're just checking what the file includes to see what's the strategy that TI suggests to include load resources in our edition. So the real-world scenario we're mimicking here is that we have, like you can see here, a digital scholarly edition of Virgil's Enid. It's encoded in TI XML. What I want to do is to include load URIs so that my software can pull information from the semantic web. So we're not exporting our data to load for this exercise. We're doing quite the contrary, which is simpler, but has a lot of potential, is we are importing data from the semantic web. So as you can see, this is a TI file. If you scroll it down, or actually if you find a specific bookmark, which is paragraph sign 040. Okay, if you do a find into your TI file and you go to the point in which you have this, all right, this bookmark, so you basically do find 040, okay, you will see that we are in the body of a TI file. The body includes the first lines of Virgil's Enid, Arma virumque cano Troiaeque primus laboris. And this is a real-world scenario, right? I have names, place names, and person names. Troiae is a place name. Juno is a person name. In TI, like you already know, we can encode, we can mark up person names, place names, or other Realien, as they say in German, so real things. You can encode them with a markup that we call semantic markup, because we're marking up what they mean, not their form, but their meaning. So, for example, in TI, we have place name, the place name element, with which I mark Troiae is the name of a place. I'm zooming in. So place name is the tag that I already wrapped the word Troiae with. But if I want to link, this is semantic markup, but it's local. But what I may do is I want to link this local place name tag to a URI resource. For example, I can find a semantic web load resource, which gives a specific identifier to the ancient city of Troy, and works as a piece of a distributed database, which includes information on Troy. What's the point of this? If I put a URI, a load URI here, so if I point to a load URI, the software can pull information on Troy, can download data from this distributed database, which is the semantic web. It can download pieces of information such as the coordinates of Troy, the names of Troy in different languages, etc. Same with Juno, same with Lavinium. Now, the TI's encoding strategy to do this is quite peculiar, and it comes from an age in which all information had to be stored locally, because not only the semantic web didn't exist, we're talking of the late 80s and the early 90s, not only the semantic web didn't exist, but even the regular web didn't exist, because the web, as you know, exploded in the 90s. So the TI strategy to encode this kind of information is the one that you see in this file. Once again, this is the complete file in which I have encoded everything, whereas in the full version of this exercise, you are asked to mark up some things yourself. You see, it's over here, it's step 1. It's all described in the exercise. Anyway, going back to our XML file. What you do is place name actually points to another element within the same TI file, whose identifier is PL Troia. And this PL Troia is in the TI header. So what TI recommends to do is that you create a list of places which is in the TI header, which you find if you find 030 in the file. So if you go and find 030 in the file, you will be directed to this point of the TI file, in which you have a list of places, and you have one element place in TI for each place that you have defined. So in other words, here I have a place with a local ID, an ID which only works in this XML document, which is PL Troia, and the place name points to this local element place. But, and this is the new feature that we have developed, so to speak, in recent times, to make our digital edition explode and draw information from the internet, we can encode load URIs, such as this one, which is the load URI for Troy, in elements ITNO. So my local definition of Troy is linked to load resources via this ITNO element here. So this, for example, this here is the DBpedia URI, load URI for Troy. Just to show you, if you are following me, you can do it yourself. You can simply open this on the internet, and it will be brought to the DBpedia page showing information to humans about Troy. Here we go, about ancient Troy. These are all representations of triples making statements on Troy. So, for example, its name in English, its name in, I guess this is Norse. It's part of the historical national park of Troia. For example, all right, well, this is something else. This is a description in English prose or Italian prose. So so the first exercise I'm asking you to do with me is this: how do I find those load URIs? So let's find ways to get to know what possible load URIs are for this ancient city of Troy, so that I can include them in my digital scholarly edition. Well, this is step 2 in the exercise. So if you go to the wiki page and you follow step 2, you find ways, 3 different ways to find what a load URI for Juno, for Troy, for Lavinium, or for Italy can be. There are 3 ways to do this, 3 approaches. There are more, obviously, but I'm showing you 3 ones. The first one is using this link, so this tool, which is called DBpedia Lookup. If you click on it and you open it, the DBpedia Lookup is a simple web page which looks like a search engine, and I can write down a string such as Troia or Troy in English, and I use it exactly like Google, pretty much, and I find, like you see, a number of things, because what I'm doing is pretty much searching in the labels, mostly labels of load entities which include the string Troy. And the one I'm looking for is this one, the second one, Troy. What you see here is the the DBpedia URI. So if I copy this and I put it aside, I see that it has a specific schema, so to speak, which is this: HTTP without S, dbpedia.org, then resource Troy. If I click on it, however, if you go ahead and click on it, you see that the page with the description of this entity, with the visualization of this data, appears, but its URL is different. It's HTTP. Okay, copy and paste it. The web page has URL. See, it's different. It's HTTPS. Here we have page. So this is the URL that shows me the information, whereas this is the actual load URI. Now, whenever I want to use the URI, I have to use the first one. What I'm seeing right here is not the database. It's a visualization of the data included in DBpedia. It's a visualization of those triples, of those statements, such that I can see this in different formats here. Since you have seen turtle before, I can click on turtle, all right, and I have a different visualization. Well, way less user-friendly, right? This is way less user-friendly than this. But what I see here is just HTML that's been produced so that I, as a human, can read it. Whereas this is the turtle TTL, you see here, turtle linearization of this data. Like Daniele said earlier, prefix FOAF means this, prefix Wikipedia makes this, blah, blah, blah. And then we have prefix Francus, subject, DBO has wiki page, wiki link, so statement, DBR Troy, object. So now I have, this is the first way to find URIs for something. First off, I choose a triple store, as they call it, so a specific load resource such as Wikipedia. There are many others, such as Pleiades, Wikidata, and many others. I choose one, and I use tools such as the DBpedia lookup. Other tools have, other resources have other tools to query the triple store. We call triple store a bunch of triples, store meaning that they're stored and you can access them, so the name is triple store. The second way is the geek way, the geek approach, which is to use the Sparkle query, a Sparkle query. Daniele earlier mentioned this query language. It's called Sparkle, which is quite complicated to learn, but not much more than other query languages. Now, this other web page, this other resource is called DBpedia Sparkle Query. You can click on it. Okay, Sparkle Query Editor. In this box, you can enter your query in Sparkle language. Go ahead and just copy paste the one that I prepared. Here we go. Let's take a closer look at it. This is the query. What it means is that I'm looking for something, that I'm filtering the data so that the label must include the string Troy in English, pretty much. So if you're following what I'm doing, open the DBpedia Sparkle Query Editor, paste the query that I already created, execute query. So what are we doing? We have a scholarly digital edition. We want to include load the URIs in my edition. How do I look for the URIs? These are the ways that we're going over. So again, thanks to the more precise and specific query that I submitted, which is created in Sparkle, I only have two results here. One is a category in DBpedia, the other one is the actual Troy. And once again, I copy paste this in my digital scholarly edition. See, it's the same URI that I had found before. A third way to do this, to add load URIs to my digital scholarly editions, for example, in XML. A third way is the one that we have here. Number 3 is a production approach using a tool such as Recogito, a software. Now, with approach 1 and 2, I already knew that I wanted to query DBpedia, so a very specific triple store. I queried it throughout simple lookup, or with the geek approach with the Sparkle query. In this third approach, what I'm doing is using software, which is dedicated to this. The one that I'm showing to you now is Recogito, but there are many. Since you cannot use it because you should register by creating a free account to use Recogito, then I am simply showing to you what you can do with this tool. This is Recogito. I already have an account, but I need to log in. All right, I'm in. I already loaded my XML file. without the URIs, of course, arma virumque canotro iaique primus aboris. It identified person names, place names, and generally speaking, an NER, so named entities. So this is a named entity recognition. It recognizes named entities, realien, we say in classics. So I click on one of them, such as Troia, and well, okay, Juno, for example. All right, Juno is marked as a person because I marked it before. It did not recognize already what person it is, but so apparently it fails. Well, what's the point here? Let's see what's the problem here with Italian, for example. All right, I already did this before, so I had to delete it. Okay, Italian. Originally, it doesn't recognize it as a place. Why? Because it made it wrong, got it wrong entirely, because it's a conjugated form. It's an inflected form. It's Italian with an accusative, or the same with the Lavinia. Okay, Lavinia, that's what I wanted to show, a case in which it failed. Now, Lavinia fails because the place name is Lavinium, but here we have Lavinia, etc. It doesn't recognize it. Now, if I click on search and I write down Lavinium instead of Laviniaque, I find Lavinium exit city. So I wanted to show you this failure because I wanted to show you that tools such as Recogito are very good at doing the job for me. So what Recogito does is querying a number of load tribal stores, and it finds the correct URIs. However, with classical languages, Greek and Latin, we have an extra layer of complexity, because in English, if I look for London, it's London. It's spelled London. It's exactly the dictionary form that you would query a log resource with. However, in Latin or Greek, you find things such as Troiaque, Troiam, Italiam, or in this case, Laviniaque, which is not exactly how I am supposed to query the database. So in this case, I had to do an extra action by hand, and then I say okay, and it tagged it correctly. So the example of so these three approaches can be summarized as looking up by hand, so to speak, either via easier tools or via a Sparkle query, or using a software, which, however, with classical languages has an extra layer of complexity because ancient languages are inflected. So I want to lemmatize the text first, meaning that I want to tell the computer that Italian corresponds to the lemma form Italian. Now, I'm skipping the other passages, the other steps, which are 3 and 4 and 5, because I leave them for you to do them in your own time. There is a very detailed description, but steps 1 to 5 arrive to the point of having this markup here complete. All right, so you will be required to write this pointer here, to write this URI here, etc. I skip them because I want to go to the next to point 6. So please go to step 6 and do it with me. What we're doing from step 6 to step 8 is using this website over here. So go to step 6, website. Okay, we're using this website, which has been created by Daniele Fusi. You see here, Fusisoft. Daniele created this, which is a website which has software running in the website that elaborates processes XML-TEI, which includes load URIs. So this here on the left is our file. Well, it's actually another file, but I can load my own file going here, load XML from file, or I can use the file which is already here, because this here mentions people such as Plato and what else? Rome as well. But anyway, okay, this is also an XML TI web file, which includes URIs, load URIs such as this one, Plato. So this is the URI, load URI from DBpedia for Plato. As you see, it's defined in a person element in XML. Okay. Now, first thing we can do with this website, and you can do it along, or you can upload your own init file and do it with the init file if you're doing this at home in your own time. Anyway, since we're doing, again, a quicker version of this, we're using the file which is already there. So the first thing you want to do when you have a digital critical edition XML is obviously using a XSLT transformation sheet to transform this XML to HTML so you can show it on a web page. Now, if you click on all right, on this icon here, okay, on this icon here, transform XML with XSLT, you have the software, the website, use this XSLT to transform this XML to HTML, and the result of the transformation is visualized down here. This box appears, which has a visualization of the XML which we used to have here into something which is readable and visible. Another thing it does is that it transforms the URIs into footnotes, providing me with the URI. Now, in order to watch something more familiar, I will do something different. I use this button, load XML from file. I will load our file, the init file. Okay, here we go. Here we have arma virunque cano, etc. Arma virunque cano, etc. Again, I click on transform XML with XSLT, and this XML through this XSLT file has been transformed by my software into this, which is the incipit of the init. Arma virunque cano, troiae qui primus aboris. The XSLT included instructions to show person names such as Eunonis and place names such as Troia in a different color. But that's not all it does. As you see, it created footnotes. If I click on Troia, I go to this footnote, which show the URI that I have encoded. However, this is not enough. The power of LOD is not that I can see the URI as a human and possibly click on the URI, and yes, I land to a web page in which I can, as a human, I can read information on Troy. This is the usual Troy web page that we have seen earlier. Quite slow, but it's going to show up at some point. Yeah, okay, here we go. All right, we already know this page. But this is not the goal of LOD. LOD, like Daniele said, is not for human consumption. LOD is for a computer to get this data, process the data, and do something with the data. So in order to do that, we hit another button in this software that we see online. It's called, this is the last button, parse XML entities. You see, we have a map here, but it's empty. We have a details box, it's empty. If I click on parse XML entities, it takes some time because it's processing, and it has populated a table, one for each person, Uno, or place, Italia, that were included in the TI XML. In fact, if I click on person Uno, on this view details icon, it's loading, it's doing something. What is it doing? It's going to, the software is using the URI to reach the tribal store, which is DBpedia. And here we go, it did it. It downloaded the title, the abstract in English, the abstract in Italian. It's taking some time because it's opening it to download it. What it is doing right now is pulling information from, here we go, from DBpedia. So you have to imagine DBpedia not as what you're seeing right now, which is a web page. It's probably more productive to see the turtle visualization. It's a distributed data. It's a piece of a distributed database. So here we go. What it did is downloading the title, and unfortunately not the abstract, of that entity, which is Juno. And it also downloaded this image. I did not encode this information, Juno is a goddess in the ancient Roman religion, in my digital scholarly edition TI. I did not put a footnote in which I wrote this information. I only inserted the load URI pointing to the load resource, which is DBpedia in this case. It could be whatever other load resource, such as Pleiades, such as the Wikidata or anything else. What the software did is leveraging the power of load and pulling that data down from the semantic web. Now, here we have another row for Italia. It's been generated by the software. If I click on View Details, again, loading, it downloads the title, a description in English, and an image for Italy. And then I can click on Italian. It goes to DBpedia again. It takes a little bit of time, and it downloads the Italian abstract for l'Italia, ufficialmente, Repubblica Italiana, etc. Not only that, but there is a piece of information that the load resource in DBpedia for Italia has, which is the coordinates, latitude and longitude, the position of Italia in the map of the world. In fact, if I click on this fly to this location icon, okay, you probably haven't seen it, so I have to zoom out again. Now we are over Asia, right? But if I click on fly to this location, and this is Italy, it repositions the map on Italy. So place, didn't work out. Place Lavinium, okay, it flies over Lavinium, which is in Latium. Troia, I click, and the map flies there, and it's a nice effect. But what's underlining here, what's behind this, is that the map can zoom the place where Troy is because it has the coordinates, the geographic coordinates. But I did not include those coordinates in my TI edition here. All I did was inserting the DBpedia URI and the BF URI, and this software here that Daniele wrote uses that URI to get information not from a static database, but from the distributed database that we call linked open data or semantic web. The linked open data is a specific implementation of the semantic web. Okay, so this was the shorter version of the exercise. Again, the point of the full exercise asks you to complete the markup of this file by yourself, step 1. Step 2, to find the relevant URIs in DBpedia in one of those three, using one of those three strategies. Step 3 and the next ones ask you to complete the markup entirely. And then from step 6 forward, you can upload your own file to Daniele's website, and you can have the software process that those load URIs for you so that it pulls data from the internet. That's pretty much it. Thank you.
Thank you very much, Paolo. Wait, I'm trying to remove your screen from the stage. Thank you so much. This was so rich and intense and always enlightening. And we do have 16 minutes for questions from the from the public. And of course, as you know by now, if you would like to ask something to our speakers, please write it in the chat box. And otherwise, as we usually do, we will abuse our power of chair persons and ask many questions ourselves. Yeah, let's wait for a couple of seconds, because I do have a question that's just out of my ignorance in this specific topic. So I think I will just go ahead. You mentioned a very a word which is very close to my heart, which is lemmatization. And that's something that, of course, everybody in digital philology is very fond of. And as you know, I always have to let's say, to reduct everything to seals, as always. And we, in the framework of the project that unfortunately just ended, so 3 years just went by, we had also in mind to lemmatize all the texts of our seals. But we, I mean, we work with CGDoc, which is a subset of Epidoc, so pure XML. And we, at the end of the day, long story short, we decided not to lemmatize anymore, because even if the texts are very short, lemmatizing everything would have made them very clunky. Yes, so it's not a question; it's a thought. How do we solve this problem of the clunkiness of the code after lemmatization? And because I'm completely out of it, because I mean I wanted to do that, but at some point I said I will deal with this later.
Go ahead, Daniele. Probably the solution. But to make sure I understand, you're saying that the TI code was too clunky, so it was unreadable, full of code. Go ahead, Daniele. It's all yours.
Okay. But in this case, there are a number of approaches, but they are probably best tried with experiments, because in the end, you have to find the best strategy which fits to your scenario. In general, when you start with lemmatization, it works better in longer texts which belong maybe to literary genres and things which have been used for training the tool. And in case of Greek, of course, we are much less able to do things like that, because we have a lot of our tools in classics are dedicated to Latin in most cases. For Greek, we are in a sort of shortage of these kinds of tools. And the tools which are best used to be integrated into third-party software usually come from UDPipe, which is a set of post-taggers which are used for multiple languages and use a universal approach, a universal set of tags which can be fit to any specific language. But in this case, probably you can, given also that these texts are very peculiar and very short, you may find easier to use AI and just go, for instance, and ask Claude or any other type of AI. And you can even try to give them the image if you are particularly fond of experimentations. We tried some weeks ago with some manuscripts, and completely outside HTML software, you know very well. And Claude worked extremely well in this case. Just got the image. Of course, it consumed a lot of tokens because it's an image high res, but it works very well. So there is the potential.
And that's actually amazing what you're saying. I'm sorry to cut you. I don't want to cut you. I'm just it's AI, first thing that, of course, was brought into this discussion. It's amazing that our project started in 2022. And the jump, I mean, it was not even, a in the realm of possibilities to do this. And of course now, I mean, it's even stupid of me to ask. I should have just tried, because as you're saying, these are very peculiar texts, and these are texts which are full of, let's say, orthographical variants, not to call them mistakes, because I mean we're talking about medieval Greek, so iota is all over the place, and we have every possible way of misspelling longs and shorts. So lemmatization is actually crucial in this respect. And but yeah, no, it's also interesting in terms of
Yeah, in this case, probably the best approach is combining an algorithmic approach for pre-processing text and a probabilistic approach, which is AI itself, which does the heavy part of the job. But this is a problem also for manuscripts, because, as you know, there are a lot of variants which just reflect a different pronunciation, which may be local or connected to a specific time. And these are also interesting to collect just for the purpose of maybe studying tradition of different kind of languages. And so in this case, we may want to have a specialized tool which is able to understand these kind of variations and provide maybe a more normalized text to AI, which just gets into processing, but still preserve these kind of variations which are useful on the historical and linguistic point of view.
Of course, and also in terms of, I mean, in terms of seals, just circling back to seals, because they are not, they don't have a tradition. They're just like what is left of the document. It's I have this crazy idea that it might be interesting to do lemmatization on a bulk of seals. Also could also give insights on the level of let's say average literacy, because these are not a product of the high intellectual elite. These are just everyday instruments that might reflect in a more, let's say, yeah, a more impartial way how actually literacy might have worked. But this is just but yes, so I will try and combine a couple
You
of.
should also try to give the AI some examples you provide for training and skills, so it can just draw from them.
That's
I can add one thing, that working with Greek working more with classical Greek, so definitely so we have training data, we have data, so you could conceive this as a separate project for adding linguistic annotations on your corpus, Martina, and part of it, of course, is normalization, and then linguistic analysis. Definitely normalization. The AI partly relies on this data produced in the past, but then is not only a problem of a specific Greek or normalization. Lemmatization is complex in any case, even if you have data, because then you need disambiguation, and then what do we mean by lemmatizing? We know. So, but I mean, it's not impossible today. And definitely, I agree. Today with the AI, we can really get very interesting and excellent results. So, I mean, don't abandon this idea, but of course, you should consider this as a separate project for linguistic annotations on your corpus. And we need that. We need more data for other periods of Greek.
Exactly, yeah, but that we have a comment, but and that's pretty much why we didn't go ahead with it, because we understood it's a whole separate thing. It's too big to be done on the side. But we do have a comment from our students, and I will throw them on the screen. Would you like to go ahead and read it, Daniele? Because I think it's for you.
Yeah, it's about the choice of languages available in the application is a matter of decision of the programmer. Yes, it's a matter of decision, and it's also
And
due to the fact that if I try to get all the labels in all the languages, I get a lot of results, and this slows the query down dramatically. As you have seen already, we have already some problems of low performance on the Wikipedia servers because, of course, they are public services which can be used by everyone. So I just chose to limit ourselves to these two languages because they are the languages used in the Venice summer school, and I created the application for that occasion.
and I think there's a follow-up on that comment. So
yeah, English and Italian for the same reason. It's the pre-selected filter in the Sparkle query, which is built by the software when it connects to the load service.
But I think that next week we will see a session on Wikidata where we have structured data. So this is where, of course, and this is the same also with Wikipedia. So this is where you should work on the statements and properties and then select what you're interested in. For example, Wikipedia pages in different other languages, Italian, English, German, or whatever. And the language of these statements is really very rich, and which means that you have to work quite a lot on what you are looking for to represent.
Yeah, also because Wikipedia is something which has been derived from the text of Wikipedia, so it's full of garbage inside it. While Wikimedia instead is something which is born in this form, and so it's much cleaner if you have, of course, the stuff you want to get from them, because it's not as wide as Wikipedia in the end.
Anyway, if I may add on unless you have another comment, of course.
no, you can go ahead.
I mean, it's true that lemmatization, linguistic annotation is another layer, but I think that AI is helping us to do a lot of stuff. And now we're getting to a point in which was your original question, Martina, the data is, the TI code is unreadable, it's too complex. Well, if the TI is hindering us, let's use something else, right? Or we use external markup. The point is that we need layers of representation of the text, which is an old love of mine, a youth passion of mine. I've been writing a lot about this. So we need a layer of the text in which we represent the word Troiae as lemma Troia. Another layer, which is much lower, in which we have a hyper-diplomatic representation of the text because of the research questions you, Martina, are asking about literacy and stuff. So we need to adapt our data model to our scientific needs and not the other way around.
Not the other way around.
And yet you have to write TI code by hand. Existed into another geological era, which was 3 years ago, in which we didn't have AI. Now AI makes it possible to extract and produce a huge amount of data, which is basically what we need to make meaningful research, because that's the point. After you have encoded your TI file, then so what? What do you do with it? You can only do meaningful processing, including simply linking to load URIs, only if you have processed that data and have data on different layers. So I think, yes, that we should really get rid of the idea that the TI code must be human readable all the time, if it must be rich enough to make sense and allow us to create new knowledge.
No, but I fully agree. Our concern back then, 3 years ago, was really a concern of time, because we were doing this pretty much by hand, and since we wanted to address some questions, some specific questions, we were tagging even all articles. So it was starting to be a bit too time consuming. But now, as you say, I mean, I'm also a big fan of layered data, because otherwise, I mean, why are we doing this?
But that, of course, but in the end, the idea is the same. So of course, you started by hand, and now we have AI as augmented intelligence. We can consider this. So is helping us. So we started by hand, but again, annotation layers, this is important. We can add potentially infinite layers. This is very interesting. Of course, this is difficult for us to conceive that, especially because we were born in a printed age. So we are moving to a new age, but this is, I mean, it is the same. Of course, now we can speed up the process. Yeah, I think.
Yeah. And I think that we will learn more on this next week because we have a very nice session on Wikidata queries for Greek and Latin philology, which will be held by Monica and another colleague, Camillo Pellizzari from Pisa. So I think that this discussion, which sadly has to end now because it's 7 p.m., will continue next week. But please,
just one thing. So thank you, Paolo and Daniele, because this was a fantastic introduction. And I have to say more than that, to linked open data in general. So thank you also because you facilitate our work for next week. But this is really an excellent session. So thank you for doing that for Sunoikis. It's very, very clear. Of course, I understand that maybe especially for the students, now you feel a bit overloaded, but it was very, very clear step by step with complex examples and also the exercise. So really, thank you because, yeah.
Thank you very much for having us.
And I have the feeling that this session will be reused a lot in the future. That's for sure. So, and with this, I think we can say goodbye to both Paolo and Daniele. So also from me, thank you so much, and thank you to the public. And we will see you next Tuesday. On May 19th, 2026, for a session on Wikidata queries, as I said a second ago. So thank you, everybody, and good night. Bye-bye.
Bye. Thank you.
Bye-bye.